We are going to review chapter 27 that is about magnetic field. There are several key points that we are going to review. The first key point is, in the case that you imagine that V is existing, V exists because it's been created by a magnet that doesn't appear here. The first question is, if a charge is moving in some direction, V, velocity V, what is the force that is acting on this charge? And the force will be this one. We will review it with detail. The second question is magnetic field and flux. We will review again the concept of flux of magnetic flux, and we will find that the second Gauss law says that the flux of B is zero over any closed surface, any closed, wherever you put. We will see magnetic field, motion of a magnetic motion of charges that are moving in a magnetic field that are perpendicular to the velocity, and we will find that the radius is this one. We will find the force on a conductor, on a small length of a small conductor of length L. What is the total force acting that a magnetic field will produce on the length of the conductor, on the length of the particles that are moving with velocity v? This equation will be the same one than this equation. It will be the same one. And the second thing that we will find is, if we have a loop like this one and exists a magnetic field, in this case it is supposed to be in the theta axis, going up. This is the x, this is the x-axis, this is the y, in the theta axis. If V exists in the theta axis, we will see that when the current is installed in a magnetic dipole, this kind of object that is like an atom. They have current, they have electrons moving around in a circle. In this case, this is a rectangular loop, and is acting magnetic force on the rectangular loop, and they produce a torque. We will find that the torque is mu cross V, and we will find that the potential energy is minus mu dot B. So this is the equation that we will find, and this is an electrical motor. The electrical motors work in, there is a current here flowing, and there is a magnet. It means that there is a magnetic field in between the currents, and applying what is happening on this loop, we will see that there is a torque acting on the current, on the loop of current, that makes, if you change the direction of the currents in a certain time, it makes the loop of currents to run and rotate like electric motors. This is an electrical motors. So we'll see everything quickly. The first things that you have to take care in magnetic force is that the force is not acting on the direction of V, of the magnetic field. The force is always acting in the plane perpendicular to V and to the velocity. So this is the plane that the vector of magnetic field is doing with the vector velocity. And the force is always perpendicular. The question if it's going up or if it's going down is being solved in knowing how to make the cross product V cross V. And the cross product V cross V, you make it with the rule of your right hand. You take the V with your fingers and you rotate through the magnetic field, and your thumb is pointing in the direction of the force, V cross V. Of course, if Q is negative, this force will not go in this direction, will go in the opposite direction as this picture, so you have to be careful. So this is the first key idea that you have to know. The force acting on a particle q that is moving with velocity v is qv cross v. So if v is parallel to the magnetic field, the force is zero, okay? If v is perpendicular to the magnetic field, the force is maximum. And the magnitude of the force is q, the magnitude of p by the magnitude of the magnetic field by the sine of the angle that they form. When the angle is 90 degrees, the sine of 90 will be 1 and the force will be maximum. Going to define the flux of magnetic field as equally as the flux of the electrical field. The flux of the electrical field was the integral over a surface. It doesn't have to be close to define a flux. Over a surface S of E scalar dds. And the flux of magnetic field is V scalar dds. It's the same idea, is the integral, is the summation of all the V sub I, V, magnitude of V, by cosine of alpha by dds, where you imagine that there is a small dds, this is the U sub n, so this is the, let's say this is the V, so the V, so you will have to find the V parallel to U sub n. V cosine of alpha is the V parallel to U sub n. So the flux of magnetic field can be visualized like magnetic field lines. So you imagine a magnet, for example, from the magnet will come magnetic field lines. The field lines will be like this, but pay attention. At this point, the magnetic field B is like this. At this point, the magnetic field B is like this. But the force that is acting on a charge Q, we don't know to where it is unless you tell me in what direction is moving the particle. And now the force will be B cross V, and it will be perpendicular to V, V cross V, Q, V cross V. So the lines of magnetic field differ with the lines of electrical field because it's true that the tangent to the line is the magnetic field, but it's not true that the force is also tangent to the lines. So this is the idea that the lines are close, so the flux of magnetic field B scalar dds over a closed surface. Wherever you put the closed surface, there will be flux entering and flux going out, and the total flux will be zero. And this is the second law of Maxwell. The second law of Maxwell say that basically the lines of magnetic field are always closed line, wherever you put the direction, and are closed line, and you cannot divide the north and the south of a magnet. You can always have a closed line. So these are the lines of magnetic field, and let me see, and that's all. That's all. This is the flux V. You see, this is the V. This is the V, V. And the V, he called the V perpendicular, B, that is perpendicular to the vector U sub n, perpendicular to the surface. And the flux is the sum of V sub I, the magnetic field that exists there, by dda sub I by the cosine of alpha sub I. So you sum over all the surface, the V by dda sub I, and you sum it and you obtain the total flux. If the surface is closed, the total flux will be zero. if the surface is closed. If it's not closed, it doesn't have to be zero. The third concept that you have to understand is the following one. When you have a magnetic field, in this case, it meaning that it's crossing my screen, going down into my screen. If a particle arrives in this direction, the direction of the particle will be deflected by the force, because the force will be QB cross V. The force will be QV cross V. In this case, V is going to the right, but the magnetic field is going into the page. So V cross V, you make the rotation of V cross V, you make the cross product, will make a force F. And a force that is perpendicular to the vector velocity cannot increase the magnitude of the vector velocity. So what it will do, the force, it will change the direction of the velocity, only change the direction of the velocity, so it will make a circular motion inside, submerged in the magnetic field. So this will be the motion of the particles that is moving with certain velocity v in the presence of a magnetic field. So from this equation, we can find that the magnitude of the force that is always perpendicular to the direction of the velocity is QVV, because the angle that they form the velocity and the magnetic field is 90 degrees, and sine of 90 degrees will be 1. So I don't need to prove it. So in this case that the object is making a circular motion, this is the force is equal to the mass of the particle that is moving. If it's an electron, will be the mass of the electron by the acceleration of the electron. If it's a proton, will be the mass of the proton by the acceleration of the proton. But the acceleration in a circular motion is the centripetal acceleration, so will be mv squared divided by r. This is the magnitude of the centripetal acceleration. So the equation that we will have is that QBB will be mv squared divided by r. 1v will go out, and the equation will be Q by B will be mv divided by r. Now, with this equation, we have that the radius r of the orbit that the object is going to do depends on the relation Q divided by m. Q divided by m, or m divided by q, n divided by q, m divided by q, and is proportional to v divided by v. M divided by q, exactly, m divided by q, v divided by v. Okay, and this is the radius. The radius is the momentum divided by qb, mv. The momentum of the particle, and the magnitude of the momentum of the particle is not being changed, because the mass, I suppose, that will not change, and the magnitude of the velocity will not change, because the force is perpendicular to the velocity. So this will be the radius. So this is the second key concept, or the third, I don't remember. The third concept is the velocity selector. Imagine that a particle of velocity v is moving in this direction. So this is the magnetic field V. So the force will be B cross V, will generate a magnetic force in this direction if the charge is positive, of course. So the force will be to the left, QVV, QB cross V, and the magnitude of the force will be QVV. So if I don't want this particle to be deflected, not to make a circle, a circumference of radius r, I want to go straight, I need to apply to the particle still of a magnetic field. I need to superpose another force. And what force? The force should be this force of the same value. So it will be an electrical force Q by E. If I put positive charge here and negative charge here, and I create an electrical field E going like this, I will have a force F on the particle that will be Q by E. So now the particle will have a magnetic force QVV to the right, to the left, and an electrical force Q by E, in a way that if the two forces are equal, there will not be acceleration to anywhere. So the particle will continue with the same velocity, constant velocity, without being deflected. In this case, the condition is that QVV equal Q by E. So the condition is that the electrical field should be V by V. And this is the selector. You select electrical field and magnetic field in a way that V will not be deflected if the relation between E and V take place like this.